I'm going to start this week off with the same example that we left off with last week with the formic acid and the sodium formate. Remember we talked about it with the ants and how their bites are based off of this acid-base reaction. And this time what I want to look at is what impact is adding formic acid going to have on solution. Is it going to make it acidic, basic, neutral, or you can't tell? Well, hopefully when you look at this and you see the name acid in there, it's not a strong acid. That means it's going to be a weak acid, and I'm going to break that hydrogen-oxygen bond. And so what's this going to give me? This is going to be like HCOO plus water. That in a phase label. And it's going to go in equilibrium to, let's see, I'm donating a hydrogen to the water. So that is going to give me my conjugate base of my formate, COO minus, plus my H3O plus. This is the hydrolysis reaction of formic acid. All right. Well, I've generated H3O plus, so I have made it more acidic. And my sodium formate, well, that's just going to be going in the opposite direction. So if I add that to solution, what's going to do? Oh, liquid. H2O liquid. Let's see. It can't break this hydrogen-carbon bond in water, but it can accept a hydrogen. So I'm going to reform my formic acid, my weak acid. Aqueous. Plus, well, now I've lost a hydrogen off of my water, so I've made OH minus aqueous. So I have made it more basic. B. What we're going to do now is look at this in terms of what we call a buffer solution. And a buffer solution is going to have both the weak acid and its conjugate base mixed in a proportion amount that we're going to talk about here in a little bit. So first, let's just kind of tackle this problem as I'm going to borrow this from up here. Oops. Talk about this in terms of the way we have done it previously. So before, what we would do, we just look at this and we'd say, okay, let's do our rice table. I'm going to erase my little arrows. They're not in the way. I have 0.025 molar of the formic acid and 0.025 molar of the formate. So I'm going to start with those two concentrations here and here. And I want to know what the actual pH of the solution would be. Well, first, do you think it's going to make it acidic, basic, neutral, or you can't tell? Well, I can look at the Ka and I can remind myself, because then remember on the previous slide, we were looking at it going both ways, right? If it went this way, then I was making it more basic. If it went with this reaction, I was making it more acidic. And before we talked about comparing Ka and Kb values to see which reaction is going to be more favorable. So what would be my Kb? Because it's the same compound, just the conjugate base of the weak acid. So Kb, remember, is going to be Ka divided by Kw, because Ka times Kb equals Kw. I just want to show that. So Kb is going to be, let's see, you haven't been told anything about temperature, so Kw is 10 to the negative 14, divided by my Ka of 1.7 times 10 to the negative 4. And then I can do my just rough approximation. What's going to happen, this 10 to the negative 4 is going to come up top, so I'm going to have like 1 over 1.7 times 10 to the negative 4 becomes positive up top, so this is times 10 to the negative 10. The 1 divided by 1.7, that's going to be close to 0.5, so this is going to be like 5-ish times 10 to the negative 11. Kb is smaller than smaller than Ka. If it's smaller than Ka, then it means this is going to be the favorable reaction. So that is the reaction that we'll focus on with the sodium formate being added. And then you might be tempted to be like, but if I have my formic acid and I'm going to put it in solution and then I add sodium formate, well, I've done the common ion effect, and therefore I'm going to shift my equilibrium like that way, right? But the problem is I'm not actually starting off with any hydronium. This is going to be like that instant I'm adding it to solution, therefore I'm not starting off with any acid to begin with. So if that's the case, what I can't do is go in this direction, right? Because I would be making a negative concentration of my hydronium, and that's not going to happen. So I know it has to be going to the right. So this would be like a plus X. Let me write my rice, my initial, my change. My water doesn't get included. And then this would be ups, plus X. No, minus X. The equilibrium is going that away. And this would be my plus X. And then this would be a plus X. And I come down here and I say, okay, so my equilibrium is this 0.025 minus X, 0.025 plus X, and then X. And then remember, we can do our approximation of can I ignore there we go, ignore my minus X. And how do we do that? Well, let's see, I have two sig figs. So I need to know, is my initial concentration of 0.025 divided by the Ka, my 1.74, 1.7 times 10 to the negative 4, is this greater than 10 to the 2 sig figs is 100, so 10 to the 2. And indeed it is. It's like 140 or something like that. This one would be one of those where I'd be a little bit more nervous because I'm going to have 0.025, so a number smaller than 1 by 2 decimal places. So doing my trick of just looking at the exponent would make me a little nervous. I would actually want to button push that to confirm it. So I can ignore the minus X. What about the plus X? Now, I can't ignore this plus X, right? Because I'm going to have some change greater than 0. So that wouldn't be helpful at all. But what about this? Do you think we're going to change that concentration that much if by subtracting it, it's negligible? Well, then the same applies to the plus X. So that means I can ignore both the minus and the plus, but only this plus X, and only that minus X. Let me write this a different way. I'm going to write this as my weak acid, HA, and remind me that we can call this my minus A. I do not know why that just happened. Oh, I just totally erased that line for some reason. 0.025. And then this is just my H3O+. So let's write out our K. Oops. Sorry, don't know what is going on with my computer. I think it's haunted. That was weird. We can ignore that, and we can ignore that. And my Ka then is going to look like what? It's going to look like my Q that I wrote up top. It is also now gone. That is so weird. Is going to be my H3O+. So actually, we'll start with the conjugate base. Times H3O+. Divided by my acid. And so what does this look like? This looks like Ka equals, let's see, I'm going to have 0.025 times X divided by 0.025. Oh dear, they cancel out. So that means my hydronium concentration is indeed just my Ka. So X equals 1.7 times 10 to the negative 4. I want my pH. So remember, I can go, so negative log of my hydronium concentration, will equal my pH. So negative log of 1.7 times 10 to the negative 4. Look at this. 1.71 is bigger. I'm sorry, 1.7 is bigger than 1 times 10 to the negative 4. If this is 1 times 10 to the negative 4, then my pH would be 4. So I'm going to expect it to be a little bit smaller than 4. So somewhere in the 3-ish neighborhood. And indeed it is. It is 3.77. So I did the negative log of my Ka. My Ka has 2 sig figs, so my pH has 2 sig figs after the decimal. Okay, let's kind of look at this slightly different. I am going to move this, give myself some room. Let's move this up here. I want to rewrite out my Ka in terms of just my HA and my A minus. So I'll have like Ka equals my H, or A minus, times H3O plus divided by my HA. There's a reason I want to do this, because what I want to do is start solving for things. And one of the things I can do is like take the negative log of both sides. And before I do that, I want to remind myself of some log properties. Let's erase this. Erase all that. And those log properties are this, that the log of A divided by B is the same as log of A minus log of B. And the log of A times B is the same as log of A, log of A plus log of B. And that's important because what I'm going to do is break my Ka down into logarithms. So I'm going to take the log of both sides. Okay, so taking the negative log of both sides, I get something like this. Negative log of Ka equals, and I'm going to group things. I'm going to group my A minus and my HA together and my H3O plus. Write out the H3O plus first, because I think that's going to make sense once I do it. If I take the negative log of hydronium, what is that? Isn't that just pH? Pretty cool. Let's see, and then plus what? The log of A divided by the log of HA. Log of, and I'm just going to leave those as, I'm sorry, my conjugate base, not A, divided by the concentration. Now, what's important to know about these is when I wrote this Ka out, that is in terms of equilibrium. But what happened to my equilibrium expression for my plus x and my minus x is that we were able to ignore the x's because of the small change. So the small change in the concentrations allowed us to look at our equilibrium in terms of our initial concentrations. So actually, let me write this a little different. So here is the concentration of my A minus initial divided by the concentration of my HA initial. This thing here, the negative log of Ka, is this thing that we call pKa. So I can rewrite this as pKa equals my negative log, oops, that should be a minus, the negative log, equals pH minus the log of these two concentrations. HA minus. And these are initial. Alright, so this expression is getting a little bit nicer-ish. Let's see, what else can I do? I can kind of rearrange this then, because what is the most common thing that we try to get to is pH. So I can rewrite this as that the pH is going to equal pKa plus the log, not lag, of my initial concentrations. So this little expression that we just wrote out here, this is called the Henderson-Hasselbalch Expression. And it makes your life a lot easier. But there's a few reasons that you need to be careful when using this. A, do note that I have the I's written, so these are initial concentrations. So in order to use initial as equilibrium, we had to have something where our approximation works. So in other words, the concentration change needs to be small. If the concentration change is small, then that allows me to use the initial concentrations and the Ka in order to determine the pH. So this thing here is Henderson-Hasselbalch, HH. And it is going to save your life, or save you some time for calculations. You'll appreciate it. What this is good for is essentially calculating pHs of buffers. So something that is going to resist change. The pH, or the concentrations are going to change by so little that we can ignore the plus and minus x. And that is what we call a buffer. Just to reemphasize, so the ratio between these two, while it didn't need to be the same, does need to be similar for this to work. And that's just the definition of a buffer. And the ionization is negligible. That is looking at whether or not we can ignore the plus or minus x. So the concentrations need to be similar, not identical, but they do need to satisfy the plus or minus x. And the thing that we just had happen up here is that the two concentrations were identical. And so the shortcut that we got there was that the pH does equal the pKa, which is nice. That one will make life easier too. And so with that, I'm going to stop there and pick up with another example.